Hi again, this is the Earth Science Clash, and welcome back, and glad you join us. We're looking at geochemistry today, and we're going to mash up, obviously, Earth science and geoscience with chemistry. Now, chemistry is a fantastic, amazing subject that you can delve as deep and as large as you want into the subjects, into different elements and different parts of chemistry, and you can relate it to really anything you want. That's why it's a major high school subject across USA, across Europe, and the whole world. It's one of those integral sciences, along with physics and biology, that students should be experiencing, should be going through. Now, it doesn't matter if you are more of a introductory level or a medium level, or you're advanced, proficient, honors, AP, or A level, or the European standards. Where it's a higher level of chemistry. And you're looking at different applications of the subject, whether it be engineering, whether it be um, biochemistry, whether it be um, industrial practices, you know. But one thing you can definitely do with chemistry is apply it to earth sciences. And when you do go into earth science in the undergraduate and postgraduate, master's, PhD level, you will amalgamate and combine all different sciences into science to explain, discuss, or research your topic. And so my experience with chemistry was, I mean, I wasn't the best student in chemistry when I was in high school. I regret that it was mostly my fault, but I also felt that my teacher wasn't very exciting. And I went to high school at a time when I didn't have the ability or the option to look through YouTube, look through videos online, and find educational videos that I could pause, play back my heart's content and learn that way and build up my knowledge. I was left with just textbooks, lectures, notes, and the ability for me to write down what the teacher was saying, which was not much. Again, mostly my fault and distractions. So what I want to start with is the basics. So if you are a introductory earth science or you have limited chemistry, this is the basics. Now, the atomic structure is seen in this very basic model where you have the red circle and the purple circle inside this black circle. The black circle is the nucleus of the atom. Okay. Now we do have subatomic particles and small particles, like the red one is the proton, which is subatomic. Sub means smaller than. So the atom is that given size or unit of measurement, and then the subatomic are the ones that are smaller than that. Okay, we've got the purple, which is going to be the neutron. I said generally because um, hydrogen doesn't have a neutron; it has a proton. And we also have the electron, which is the smaller subatomic particle that is on the outside of the nucleus flying around in its orbital shell. Now, when you learn more about chemistry, you'll learn that there's different levels of shells and how they behave around and how they are used to bond with other atoms, whether they exchange electrons or they share electrons. It's also metallic bonding as well. So, again, if you're proficient at chemistry, you know this, okay? And obviously, the combination of atoms makes molecules and compounds and mixtures, and then more complex complex chemistry follows. So, what we're going to look at is how we get different kind of elements. Okay, elements are atoms of certain sizes. Now, I say sizes because it's the size of the nucleus and the corresponding amount of electrons that fly around the outside. Okay, so if we take our basic element, all right, hydrogen, big H, all right, or H in English, all right. So hydrogen has one proton, Okay, it is the simplest as far as we know on the periodic table, and it is very abundant across the universe as we estimate based on star compositions and the universe as far as we know it. Okay, now if we add one more proton, okay, one of these lovely positive charge, there's a positive charge, there we go. Add one more, you get two of these boxes right there, and rather than call it hydrogen, we call it helium. So this is a larger element compared to hydrogen, and we call it helium. Okay, again, another abundant uh, gas element. Both these are gases in the universe, and our sun is mostly made up of these two elements, which we'll get onto in a different video. So if you keep adding the protons, you get larger and larger and larger elements that go up to 92. So there's 92 naturally occurring elements on this planet as far as we know. Now, there are a lot more than 92 on the periodic table, or because they are man-made. You know, we have intentionally created these elements, but there are 92 naturally occurring. Okay, before humans were even thought about on the planet, there were 92 natural elements. Now, there could be more out in space we're not sure about, but right now this is our current understanding. And the 92 elements make up about 99% of all the elements on the Earth. So the ones that are man-made only equate to around 1%. Okay? So this is the chemical symbol for carbon in this box here, C. So we have carbon. Okay? Now, we are carbon-based organisms. We have carbon in our cells, our DNA, our makeup, right? So in chemistry, you write each element a certain way. It's a standard way, so it's easily transferable between all the elements, so we can easily read and understand each element's characteristics. Likewise, to the bottom left, there'll be a number. This one is 6, so carbon is 6. So it's the atomic number, and the atomic number relates to the amount of protons in the element. Now, this is based on a neutral carbon, which means it is not negative, okay, not has a negative charge, and it's not a positive charge. It is in between. It is neutral. So they both cancel each other out. Negative and positive cancel each other out, so it's a neutral charge, okay? Neutral charge. All right, and the atomic mass, well, mass is the weight plus, yes, gravity as well. So the mass is going to be 12 for carbon. So we do a little simple math. 12 subtract 6 equals 6. So we had our protons. We also have find out our amount of neutrons. Okay, and usually, generally, the same amount of protons equals the same amount of electrons. So there's 6 electrons flying around the outside of this carbon atom, this carbon nucleus. So we have 6 protons, 6 neutrons, and 6 electrons. Okay, that's all good. There are a few differences, though, sometimes. Now, these are called isotopes, what I've drawn here. I've used carbon again, and here is our regular run-of-the-mill carbon. The majority of carbon that is naturally existing on Earth is in this form. So we have the 6 protons, the 6 neutrons, and the 6 electrons. Okay, so, and again, you can go into high-level chemistry and denote what these mean for the charge and the bonding characteristics and the electronegativity of each element, and really dive deep into chemistry. Right now, we'll keep it at the basics. So the isotope, as you see here, all right, so I've got 6 and 12 on the top, which is the majority one. This carbon has 6, again, the same amount of protons. In isotopes, the protons for the elements are consistent. They do not change. Okay, so 6, 6, and 6 for all 3 of these versions of carbon. Now, what does change is the mass. Okay, the atomic mass does change. Okay, as we see, 13 and the bottom one is 14. Now, This one here, the 13, okay, it's going to be what? 13 subtract 6, which equals 7. So there's 7 neutrons. So it's a heavier element. It is slightly different in the nucleus, okay? And then this one here is 14 subtract 6, which equals 8. So there's 8 neutrons. So again, we're making a larger type of carbon. Still carbon, because it has the 6 protons, but it's a larger mass. And this one in particular is very unstable. There are elements in nature that are naturally unstable and they decay. Uranium. Now, generally, they're the larger ones. They're the larger elements that have a lot of protons, the 90s, the high 80s. They're the ones that are naturally unstable. Okay, there's only a few of them, but on a very rare occasion, so less than 1%, naturally occurring, you'll find this carbon 14. Okay, this carbon 14, which is naturally unstable based on the amount of neutrons. It's too big for its size, basically, and it wants to lose a neutron, basically, and it's very unstable. So this is an isotope. So why have I discussed basic chemistry, atoms, elements, isotopes, neutral charge, positive charge, decay, time, all that stuff? Is because it's the building blocks. It is the basics. It's like if you learn to read and write, you need to learn the alphabet, the ABCs. This is the basics for geoscience, is understanding that our rocky planet is made up of atoms and elements that combine into molecules, that combine into different minerals, that combine in different rocks, and rocks form different ways and create different landforms and situations that we can study. That is the building blocks that every student has to understand, that it is a step-by-step process going from small and basic up to large and complex. And if we understand each step and can connect each step, then hopefully those complex situations and complex environments can be understood clearer or in a better way. So we're discussing the crust and upper mantle. Why? Because we're looking at magma and lava and volcanism. So the crust is our very thin, okay, it's silicate minerals. Now, silicate means that there are 2 elements that make up majority of the minerals. So these elements are inside or a part of the chemical makeup or composition of these minerals that make up our crust. Okay, it could be oceanic, continental, even lithosphere, and in many ways the asthenosphere, which makes up the upper mantle. So looking at silicon and oxygen. Okay, so to really understand the chemistry of our crust and where we get magma from, we have to appreciate the chemistry. So of the 92 elements that naturally occur on the Earth, in the crust of mantle, we're looking at 8 major elements that really make up about 95%. So 95 to 99% of all of the majority elements in the crust of mantle are these 8, as you can see, from oxygen down to magnesium. So let's look at the percentages, which is kind of awesome if you think about it. Let's start with magnesium down here. So magnesium is about 2.1. 2.1. That's in percent. Potassium, K, all right, about 2.6%. All right. Then we got sodium, about 2.8%. Calcium, looking at 3.6%. Iron, around 5%. We have aluminium or aluminum at 8%, roughly. Silicon, all right, silicon at 27.7. and our beautiful leader, which is way ahead at 46.6%. Now, combined, these two, the top two, we combined, all right, equals 75% of the elements in the crust, 2/3, all right, well, sorry, 3/4, all right, 3/4. So the rest going down here are smaller increments, very small percentages compared to the top two. Now, these two combined, okay, as you see here, silicon plus oxygen, which is SiO2, or also can be denoted as SiO4, depends on which way you write it chemically, but it's about the amount of bonded amount. Wait, sorry, guys. Amount of bonds. So generally SiO2, or you can see it written as SiO4. Either way, this is called silicate minerals, and the combination of the molecule is called silica. Silica, and we'll get more into that in terms of the magma in the magma video. So this is pretty much it. Now, if we look at oxygen in more detail. Okay, so let's draw here's the oxygen atomic nucleus, and we have on the outside we have the electron shells. Okay, there's two of them. Okay, so what we have is very basically oxygen is this one here. We have two electrons. So oxygen is 8. Oxygen is 8 and around 15.99, but generally 16. So there we have 8 protons, and we have also 8 electrons. So what happens is in the electron shell, they divide these 8 electrons between the shells. Now 2 can go in the first shell, and then we've got another 4 in the next shell. All right, so we got 4 in the next shell here, and they have the third shell. It has 2, so there's a total of 8, right? However, this third shell can hold 4, so there's 2 empty spaces left on the outside electron shell. This is why oxygen is extremely good at bonding with other elements. It's extremely what we call sticky. It has the instant availability to share, and it wants to become stable. So it's like desperate for 2 other electrons from a different atom nearby to stick to it to make it stable. So it was done that way naturally, just by pure coincidence or just design. It's beautiful where it is designed to link with other things. And when oxygen links with other elements, we call it an oxide. Okay, so this happens a lot throughout geochemistry and earth sciences, how the crust and the elements are pretty much oxides and silicate minerals. And to understand this, we can really get into the basics of geochemistry. All right, so I hope, guys, you like this. We'll get on to minerals next and how it fits in to the magma. Guys, if you want to subscribe to the video, to the channel, will be great. Please leave a comment, and look forward to seeing you in next future videos.